Hi, welcome to the first episode of Topology for the series Gravitation. First of all, we are going to take a look at why should we study topology and what does general relativity has anything to do with topology and manifolds. Well, actually, general relativity describes interaction among matter, energy, and gravitational forces. And in this theory, spacetime can be modeled by a four-dimensional manifold which carries a geometric structure called Lorentz metric. And if you're not familiar with some of these words, we are going to get through them in the next couple of episodes. But if I want to say what a Lorentz metric is, in special relativity, we have a metric called Lorentz metric, which tells us the distance between two events in space and time with coordinates like t, x, y, and z. So that's what a Lorentz metric is. And in order to understand the structure of universe, we need to understand which four manifolds can carry Lorentz metric and how topology influences the metric. And besides that, we are seeing that pure mathematics is always overlapping physics in various fields such as string theory and electrostatics, and you know what I'm talking about. And topology is basically what we need to understand manifolds. So what is topology? Well, to understand what's topology, I just want to take a look at spaces that we are familiar with, and then I tell you what a topological space is. So a topological space, we have a diagram right here, and we can see that norm vector spaces, which we have worked with them a lot, are the smallest of these three spaces, and then there is metric and there is topological spaces. So for normed vector spaces, we have a space like V, which we defined a function on this space, which we call it norm. And the way the norm works is it has these four properties. The first one is non-negativity, which means that norm of any element from our field is greater or equal to 0, then is positive definiteness, which means that the only norm which equals to 0 is the vector 0 itself. Then there is absolute homogeneity, which means that, for example, if we have this vector in our vector space, then we take the norm of it, and lambda is a member of R, then we can write it like this. These two are equal. That's what the third condition means. And then there is triangle inequality. I'm sure you're all familiar with this, but I'm gonna write it anyway, which means x plus y, the norm of x plus the norm of y, is greater or equal to x plus y, the norm of x plus y. And there are things that we need to pay attention. For example, we have to pay attention that V is a subset of some field. You can see what properties make a set to a field, but there is a big difference between a field and just an ordinary set. So let's move on from normed vector spaces and see metric spaces. So I'm just going to say what metric spaces doesn't have, or what's the difference between them. First of all, we need to pay attention to the definition of our function. As you can see, this is from one dimension to R, but here there is a Cartesian product to R. That's one difference. Then we can see that we do not have absolute homogeneity, so that's not in our metric spaces. And one last important property is that M is just an ordinary set. But D is actually really V, and it's another function to visualize the length for 2 points. But here, as you can see, vectors have only one input in the norm function. So that's what metric spaces and normed vector spaces were, and we are familiar with them. And the thing is, topological spaces are really general in the sense that they don't have non-negativity, they don't have positive definite. In fact, they don't even have a function. They are not spaces equipped with functions. And the way we work with them is just using sets, and the operation between them is just union and intersection. So let's go to the definition of topological spaces. And one last thing that I need to mention is that in topology, we just want to mess around with continuity. And if you've seen math analysis, you know what I'm talking about, because we use open spaces to conclude continuity, which in metric spaces, that continuity condition for topology is also true in metric spaces. As you can see, topological spaces are bigger than metric spaces, so that should be true. And the whole point of topology is to mess with continuity, as I said. So then there is the definition of topology. So if X is a set, a topology on X is a collection, which I call this curly T, of subsets of X satisfying the following properties. So we have 3 properties. I'm gonna go through each of them. X itself and the empty set are elements of our curly T. So basically, we have a set X, then we define a new set and put some of our sets into this new set. And the first condition tells us that X always should be in X must be in our set curly T, and so is the empty set. So these are the first condition. Then the second condition tells us that T is closed under finite intersection. So basically, let's assume that 2 sets, let's say U1 and U2, are a member of our curly T, then U1 intersection with U2 should also be a member of curly T, and by induction you can conclude this one. So so this is the necessary condition, this is the generalization, and this is the second condition. So we go through the third condition, and notice the difference that I used here arbitrary unions and there was finite unions. So there's a difference. If you have seen math analysis, you know that we can have unions based on non-countable sets. So if, like, let's take R. If we have this union, then this also should be in our set curly T. So as you can see, these spaces are really general. I mean, we don't have a lot of conditions on them. These are just open sets which interact with each other with intersections and unions. And that's it. So I'm just going to show you some examples of topological spaces to understand them and see how vast they are. So before that, let's just have two other definitions. I mean, we use this notation to show topological spaces, and we called those sets that are in T as open sets, and we define a neighborhood of P if P is a member of our space. Neighborhood of P is defined to be an open set which contains P. So that's the neighborhood. That's what neighborhood of P is, and we show it with this sign if you are in metric spaces because of this R. So generally you can say we show it like this or this. These are all appropriate notations. We have some examples. Our first example is the topological spaces which consist of X and P of X. This is the power set of X. So why this is the topological spaces? Well, let's just go through that real quick. Obviously, X is a member of power set of X, and so is the empty set. The second condition is also satisfied because we are using the power set of X. It means that every possible subset of X is in our curly T. So whatever you intersect or union does not matter, and they will all of them will be in our curly T. So that's a quick proof of this space to be a topological space, which we call it discrete space. And yeah, the next set is the next topological space is, let's assume that Y is our set, and the only thing here is the empty set. So obviously the first condition holds because empty set is a member of itself, and yeah, that seems right. And since there is empty, doesn't mean to union or intersect anything, so that's true. And I mean, such useless topological spaces. So the next one is more, I think it's better to understand what topological spaces is. So our set is simply the set of numbers 1, 2, and 3. And our curly T is this set right here. So as we can see, the intersection of these things are also a member of our curly T. You can check them. Okay, if like you intersect 1 and 2, you get 1, or do this for any of them, it will be our set, trust me. And then we have their union, which again 1 and 2, union 1 and 2 and 3 is equal to 1 and 2 and 3, and that also is in our set. And then there is a really important topology, which we call it metric topology, and we define it as the collection of all open subsets induced by our metric. So that's what the metric topology is, and you can check that if it's that topology. I will give you this as a homework. There is another phrase for that, which we say topology generated by D, and D is our metric. There is Euclidean topology, which is a metric topology Rn with Euclidean meter. And yeah, that's a topology too. So let's move on. And then there is definition. A topological space is said to be metrizable if its topology happened to be the metric topology generated by some metric on X. Well, why did we define this? Because not all topologies are metrizable, and the example for that is non-Hausdorff spaces, which you will see soon. And these spaces are really weird because there's a property which you may think that holds in all spaces. That is, you can separate 2 points, but in non-Hausdorff spaces you can't, and therefore this is not metrizable. And so not all topologies can be metrizable. You need to remember that. Then we reach our first theorem. So let's suppose that M is a set and D and D prime are 2 different metrics in M. Prove that D and D prime generates the same topology. If and only if for each X in M and each R bigger than 0, there exists R1 and R2, which the neighborhood of X with radius R1 with respect to our metric D prime is a subset of the neighborhood of X for the radius R and with respect to metric D. And this one is just the other way of the first one. Well, let's prove this theorem. I want first to do this way. Let's take D and D prime, generate our space T1 and T2. Okay, so these are the spaces generated by D, and it says that they generate the same topology. So T1 equals to T2. And what does it mean for these topologies to be equal? It means that each open subset in T1 is also an open subset in T2. Okay, so then you can easily conclude that this condition right here holds. Now let's do the other way. For the other way, we have to prove that T1 is equal to T2. Okay, so let's say that, and for doing such a thing, I say T1 is a subset of T2 and T2 is a subset of T1, and this concludes the equality. So for this part right here, I want to say that T1 is a subset of T2. What I'm going to do here is use my assumption right here. Okay, actually we have to use this one. Okay, there's a difference right here. You need to pay attention to this. Since the neighborhood of x with radius r2 in our metric D is a subset of an arbitrary radius neighborhood of x in our metric D prime, then we can say that, let's suppose that this is our metric space and this is BR, then what this thing right here is saying is my neighborhood is smaller. Okay, let's suppose that this is x. Okay, let's suppose that this is x, and it says that I can do this. So if it can do this, it can build a smaller neighborhood around that point. This means that it has more neighborhoods from our metric space D prime. So this actually means that T1 is a member of T1 is a subset of T2. And we can say the same proof for T2 being a subset of T1. And yeah, that's it. And one last thing is that we can define topological spaces on the open subsets of our space, and they will be also a topological space. That's really easy to check. You can do it if you wanted to. And thanks for watching. This is the end of episode 1.